Okay, well, good afternoon, everyone. Great to see you here. Welcome to EECS151 251A, Introduction to Digital Design and Integrated Circuit. We are actually coming to almost the end of the semester. It has been a long journey. I was chatting with some of the students earlier. I never expected that we started this semester virtually with the first couple of weeks. I welcomed all your folks virtually. Now we have to actually conclude this semester also virtually. But I think it's really exciting in the sense that we got connected. We get to experience both the virtual world for the convenience, but also in-person interaction that I get to see your faces, I know your names, and get to know you, what you're interested, what you're passionate about. I really enjoy this semester. So in today's final lecture, right, we're actually really going to talk about just a recap, what we have accomplished. People typically feel like the end of semester is always super stressful. It is, but it's also a time to really celebrate how much you folks have really accomplished in every courses and including this one. We'll also talk about some of the opportunities, both here at Berkeley, what kind of courses you can take, and also what kind of career you can pursue next. This is really an intro class, as the name suggests, but really open up really exciting opportunities that things you can do in the future. One thing I want to highlight here is we talk about the golden age of computer architecture, right? This is a really exciting time to think about hardware design, right? Like the Turing Award winner, like Hennessy and Patterson, right? Really, they were really excited about the future of hardware. A lot of exciting things we can do in building a more efficient, domain-specific, and the secure hardware platform. We'll talk about some of the opportunities there and really the long-term vision for the industry and what you can really accomplish in this industry. So we'll also do that. This is very important, and we'll see how things are actually connected with what we covered in this class and what you can do in the future. With that, let's get started. Just a quick recap. The last lecture, we talked about the other types of memory. We started with SRAM, right? How SRAM works, how different things works in SRAM. Yeah, so you folks just listen to the Turing Award lecture in one video. Yeah, then you see the connection. I'm also going to talk a little bit more about what my perspective is and how you can actually grow your career. I definitely also take a look at, watch that, hear from really the experts, right? The exciting things. We talk about the caches, right? How cache works, very important in thinking about the locality and capture locality in hardware. Also about DRAM, right? How DRAM works. We briefly talk about CAM and the flash, how it works, just for your information, right? See, when you hear those terms, these are actually very related. They can actually be organized into the tree that we showed earlier, and those are just the different components in those factors. So those are the memory arrays. We'll conclude all the technical discussions up to that point, so that we see a range of different things from combinational circuit to sequential circuit, and we go also from the high level Verilog microarchitecture all the way to CMOS, and then how we actually can use CMOS transistors to build a lot of this very important building block. So in today's lecture, I'm going to talk about some of the opportunities moving forward and also some pointers that you can take. And really, those are more like conversation starters. You can always reach out to me about specific things that you have in mind and how we can actually help you to move forward. Before we get there, right, so I think the HKN folks, they're not joining lecture anymore, but course evaluation is very important. This I mentioned last time, this is the first semester we have actually with more than 50 students enrolled in this class. We literally double the enrollment this semester, and this is almost majority of the class students are actually undergrad students. We'd like to hear how you like this semester, how things go so far, what can be improved, right? And we should also actually put in more resources in the future to grow our spring semesters as well. And 151, this is the topic of 151, something I'm very passionate about. I'm actually also going to teach this class again in the fall semester, right? What we can do to improve, how we can get more students like you get excited about hardware. So tell us what you think. This is very important. We do have some extra credit mechanism to get you more motivated to fill out the survey. So yeah, definitely do that. It's very quick. Just go through it, post your screenshot on Piazza, and you will get actual credit. So with that, we'll do a quick course recap, and we'll talk about what's next. So we have seen this slide at the very beginning, right? So we talked about this is a really course I mentioned earlier. Really discover your own creativity. I think I also mentioned before, like every design is different. Even all of you are designing a 3-stage pipeline. What you will be designing will be actually very different from each other. So this is a very creative area. You can actually put your personality into the hardware that you're designing. So that's also really the fun part of being a hardware designer. And one thing that's really important, you see the progression of this course, right? We're actually jumping like different layers, abstractions. We need to understand the fundamentals, how transistor works, why they actually connected certain way. But we also need to see high-level pictures, right? How different modules are connected so that we can develop some very programmable engine that can accomplish a range of different things, like what we do in modern processors. So a lot of this layers abstractions, how we understand different layers of abstractions, and also be very comfortable in actually jumping around at different layers abstraction. That's always one of the most important things in hardware design in general. And finally, this class is very hands-on. Like going through lecture is one thing, but labs are a very important component where in the lab you actually break things, right? You need to figure out why it doesn't work or why it works sometimes. And also debugging your circuit, maybe even helping your partners, having other folks to figure out what's actually going wrong in their design. So this is really cool where you actually get to build things, no matter whether you're in ASIC lab or FPGA lab. This is a cool part that you get to build something really fancy that hasn't been actually done before, and really embed your personality to the hardware that you're designing. So that's a really cool part of the class of hardware design, and we really need to learn by doing. And I hope at this point, at the end of the semester, right, those kind of bullet points actually make more sense to you because you see how they are connected. Abstraction, right? We talk about abstractions, and this class is mostly on the lower level side. We talk about simple in order pipeline and how we actually learn this new language Verilog, different from the languages that you have seen before, but really thinking about hardware generation. Whether you're in ASIC or FPGA lab, you will actually learn a different set of tools and how they actually synthesize the design to generate the bit streams, the GDS files, so that we can actually get something manufacturable in hardware. And we hop around the different layers to see what are the low-level implementations and how we actually also go upper levels abstraction to see how things are connected. So this is really important part of the hardware design. We need to start from specification. Even for your final project, you start from this 100-page document specification, and then all the way go through this design process. So that part is very important also in your future when you actually approach a hardware design project. With that, it's actually very important if we just think about so many things that you can do, and so many things folks are actually doing today, right? This field is very different. Before, we always like, oh, Intel, AMD, that's basically the semiconductor world. Everything is different now. Like Apple is making very impressive hardware, starting from mobile SoCs now into desktop SoCs, and all their like different hardware they're designing, leveraging different techniques. I will talk about this M1 Ultra, right? Really doing the chiplet integration. So a lot of companies are actually making their advances in building hardware. Apple is just an example, right? We also briefly mentioned Google is designing their hardware. Microsoft is designing their hardware. It's really hard this day to say which company is software company, which hardware company is hardware company, and which one is semiconductor company. Every company is very interested in this kind of full stack approach approach. We'll also talk a little bit more for your own knowledge base, right? Understanding the full stack. Of course, we want to see the application, but also understand what the hardware is, right? How you actually run your application onto the hardware will be a very important skill for everyone really in the future. And we want to provide you with this hardware, this level of hardware understanding, so that you can, maybe you're not doing hardware in the future, you also need to be a very good programmer. You also need to understand how hardware works. So that's just really important, and a lot of advances in this broader semiconductor community, not only just the traditional Intel, AMD side of the world. And also a lot of advances also from like startup, right? We talk about servers, how they actually do this kind of crazy wafer scale computing. It's very hard to imagine, right? This kind of thing is actually done in a startup, and we see a lot of activities going on, a lot of acquisition, right? That's also interesting to see the dynamics of the semiconductor industry, how the different companies actually partner with each other, especially between like processor company and FPGA company, right? We see a lot of IP consolidation, different companies trying to broaden their portfolio to have different flavors of IPs so that they can actually build this kind of heterogeneous system. We also have different techniques, right? Chiplet integration become very important so that we can integrate different heterogeneous IP blocks together. So really exciting time for both like startups, software companies, hardware companies, see the entire stack, see the interaction, and explore the opportunities that you can actually see in this area, right? So if anything, I feel definitely we are very interested in the technical aspect of things, but it's also very important to see the, I guess, not necessarily the business side, but really the implication, a lot of opportunities from startup world to like maybe even the traditional software system companies. There's a very strong interest in thinking about hardware. So keep an eye on that kind of thing. So things are changing in the way we approach innovation, in the way we build hardware. The fundamental is also changing. Like we talked a lot about like new generation of SoCs, right? With advanced technology, we're just keeping down, like thinking about the new node every year. Even the thinner scaling, it doesn't work anymore, but we're still getting very good density, right? So Intel has their agenda, TSMC, Samsung all have their agenda to keep pushing forward with a new generation technology node, right? What's the behavior? We talk about a lot with the FinFET, a lot of assumptions actually doesn't hold anymore, right? We really need to understand their behaviors and think about how we can actually take advantage of the new densities that bring with those new technology generation to build dedicated hardware, like the neural engine showing here, and also a bigger or more efficient processors take advantage of those technologies, right? So again, this is a really cool time to think about hardware design. You need to both understand the applications, but also understand the lower level component to actually do innovation in this area. So a lot of things are changing in this area, but really exciting opportunities from all like the lower end, the device end, and all the way to the application and hardware side. So before we get to the next set of topics, some announcement we'd like to make. So this will be the last lecture. We will have official, like regular lecture. We have a guest lecture next week, next Tuesday, on system Verilog. Some of the folks are going through interview process. A system Verilog question always come up, especially now you have seen actually the pros and cons of Verilog. So system Verilog is designed to address some of the concerns with Verilog. So definitely stop by. Many of our students find it very useful, even just having the understanding. It's actually very helpful for them either to learn system Verilog or go through some of the interviews, because you have at least understand the core differences. But system Verilog itself is also a huge topic. On the administrative side, we have a homework due this Friday, and we also have a new homework released, and that's due next Friday, right? So those two will be the homework 8 is more thinking combinational logic, arithmetic, and homework 9 is really thinking about sequential logic. Those are not long, and those are basically a chance to help you to review the lecture material, right? So start early and use this as an opportunity to review the material. Final checkoff is scheduled for FPGA lab and the ASIC lab, and that will be basically the well, you have the lab checkoff and the presentation. FPGA lab do the checkoff, ASIC lab do the presentation, and then we'll have the final report, and then we'll have the final, the lecture final on May 12th, and we'll also schedule a review session so you get to review different topics. So that's a plan moving forward. A lot of deadlines, but again, this is just to help you keep everything on track. Definitely wrap up the homework. Those are supposed to be short, give you opportunity to review different topics, and then the focus should be on the project. And then by the end of the reading period, we'll get all the project topic wrap up, and then you folks can focus on the final. So before I move on, questions, comments, anything you have in mind? Makes sense? Okay, another way, just also use Piazza or send me email, anything, right, about the class, and let us know what you have in mind. Yeah, for both labs, a lot of you are actually reaching out about what counted as actual credits for the lab. Yeah, feel free to reach out. We actually cut a lot of IO stuff for this semester, and we want you to do actually more optimization, right? I think that fits that you are more passionate about. So if you have bandwidth, you want to do more actual credit stuff, we welcome, and I think it's a good way to actually again add even more personality to your design. Okay, so that's all the announcement, and I do want to have enough time to talk about next. So we'll talk about what are the things you folks, all of you can do moving forward in both courses, and also opportunities in thinking about hardware design in general. So the course roadmap, I think some of you have seen this before. Some of you have maybe not. So this is a more course roadmap thinking about circuit and hardware, right? So this is more focused on the circuit and hardware component. So we are here. So this is EECS151 to 51A, really thinking about digital logic design, right? So although 16A and B are labeled as prerequisites, there's a real prerequisite at this point, many of you probably also know, is 61C, right? So many of our students are just very excited about the topic after 61C, and you folks are basically the target audience. We'd like you to bring you to go deeper to see how hardware is actually designed, and really design a piece of hardware of your own in this class. Right, what's next after that if you are also interested in exploring other things? So some folks mentioned, like Brenda mentioned 152, right? Some of you are taking this concurrently. Some of you have done 152, now doing 151. And some of you actually may be interested in doing 152 next, right? So this is a natural next step in thinking about more advanced computer architecture stuff, virtual memory, memory cache coherence, out of order execution. So that's basically all the important components in building modern processors that will be covered in 151. 151 is offered every spring. So keep in mind, so if you're interested, you can do 151 next spring. So this will be in spring 2023. So that's one class to consider. Another class to consider is 251B. So this will talk about more advanced systems. So this will also offered in 2023. I know somehow it's actually listed in some versions of course planning. It won't be offered this fall. It will be offered next spring, and I will be teaching that class next spring. So looking forward to see at least some of you in that class. So that class will go deeper in some of the optimizations. For example, we actually haven't done, we talked briefly about low power design, but we didn't actually talk a lot like how it works, how we actually can do DVFS, can we actually design low power circuits, low power architecture. We didn't actually go a lot about that. SRAM, there are also a lot of SRAM related reliability, readability, variation, or the component related to SRAM. We also didn't get a chance to do that, right? So that's a natural step. After this class, you are interested in actually understand deeper how we can actually do this advanced optimization to see more other component, that will be EECS151B. Undergrads can also take this class, so just reach out to me. 151 is basically the prerequisite. I'll give you code so you can get enrolled. So that's the class for also direct follow-up for this one. And another class I strongly recommend you folks to take is, I guess it's called Advanced Topic in Circuit Design, but this is basically the tape-out class. It's really two things, both tape-out and bring up. So tape-out will be in the spring 23, and bring up, there should be one in 2022. I know it's like the course hasn't been listed yet. Professor Niklich will be organizing that course that will be listed eventually. So it will be a good opportunity to take it. Even you haven't done the tape-out class, you can actually do the bring up class first. You see what are the concerns in bringing up the chip, and then you will be better prepared to do the tape-out class next spring, right? So you could either do tape-out class first and then do the bring up class next. Then you design your chip and then bring up your chip. Then alternatively, you could actually, depending on your schedule, right? You could actually do bring up class first, bring up like one of the chips they're currently being designed. And then you see what are the issues, how you can actually design your chip better to make the bring up easier. And then you can do the bring up the tape out class next spring, and then to design your own chip, right? Again, for this one, 151 is basically one of the prerequisites, and after 151, you are very prepared to do that. So those are the, I guess, the direct follow-up classes. If you are interested in EE side of things, circuit side of things, there are also a range of other things. Like we used to actually have prerequisite from 105, but we actually removed that prerequisite. What I actually observed is that some of our students after 151, they got interested in 105 because they actually want to see how like circuit actually works, how the CMOS transistor actually works, how we actually build the different components. Then they actually take 105 after 151, right? So that's also a pass. This like a lot of the CMOS and circuit stuff, we actually stay purely at the digital logic level, right? We go a little bit about current and voltage, but we actually didn't go too much. We most just a high level RC analysis, right? If you are interested, 105 is also a great class to actually go deeper, especially it's very related to a lot of the real ASIC design and what are the interactions there. So 105 is a great class. I know the instructors of 105 have been doing a lot of experiment to revamp 105 to also take students with a wide range of background, especially more CS background. So 105 is also a very interesting class if you folks are interested. And then you're interested in analog, 140, 240A, right? Those are also another very good class to see analog aspect. So I'll spend a little bit more time talking about the left half because those are more, I guess, digital circuit related, but then there is also analog, power electronics, and even fabrication. Some folks actually take 143 for fabrication. That's also really cool. You actually go into the fab to actually fabricate your hardware, right? So that's also things that you can consider. There are also a couple special topics class I'll mention later. Also something you folks can take if you are interested. Before I move on, any questions and thoughts? Anything you want to share about the roadmap?
For the bring up class, where that is that 290C or 194 again?
So it's both. For undergrad, you folks do 194. For grad students, it's 290C. It's the same class. You just have two different course number.
And the bring up portion is because you said that the tape out class is different from yeah, the 194 is the tape out class, but the bring up is which one again?
No. So both tape out and bring up will be a special topic class. So it will be 194 and the 290. The two different course number is just for undergrad and the grad students, but they are the same course. It's not listed yet for fall 2022. Professor Niklich is working on that. He will get that listed at some point, but it will be a special topic class. So you.
All right, thank you.
It's not online yet, but it will be online soon.
Thank you.
Any other questions or comments?
Yeah, can you explain a bit further what do we do in the bring up class?
Yeah, this
Like
is
other
this.
than bring up.
That's a good question because this will be the first semester this bring up class will be offered. So I think there's definitely a lot of unknown. I know some folks are actually, I guess a better source is to actually talk to the students who are in the process of bringing up last year's tape out. I think you will be involved with a lot of application, how you actually run application, how you will need to do a lot of FPGA emulation, just because if something doesn't work, right, you either go through simulation or go through FPGA emulation to see what are the reasons. So it's sometimes maybe like a software engineering class, but you will do actually a lot of either reverse engineering or debugging to make sure why things doesn't work. You will also do a lot of bench work, just see, get things in and out, making sure whether it either is expected or not expected. So this will be a very hands-on class. Again, very open-ended, depends on what will be so if the problem is something that you can recreate it with RTL simulation, you'll be mostly doing the simulation portion of it. If this is actually hard to simulate, and you actually need to run end-to-end application, you will need to spend a lot of time actually doing FPGA emulation because that's actually more efficient in testing the errors. And there will also be 2 chips that being done in this year. Currently the K-pop class, one is actually more analog focused, the other is actually more digital focused. For the digital focus, there will be general purpose tile. There's a RISC-V component, there's a system component, the last level cache, system interconnect, tile link. I think there's also an accelerator component, but I'm not sure whether they did a machine learning or matrix multiply accelerator or some kind of encryption accelerator. So there is also an accelerator related. Then my expectation is the way they will run the bring up class. They will also divide team up, whether you will be mostly focusing on bring up the RISC-V core or focusing on bring up some like accelerators or making sure like the system level interconnect is running, or and maybe even bring up the clock, the initial bring up. So all those will be involved. So it depends on which chip will be used and what would be the issues of the chip. But it will be a lot of debugging, understanding what the problem is, and debugging and do a lot of guessing and try different things in simulation, FPGA emulation on the chip benchwork to see what's involved. So it's very open-ended. It will be the first time we run this class. I think it will be fun just to see what can break a chip. So very likely there will be bugs in this chip, I think. But a lot of that part is to understand where the bug is coming from and thinking about ideas to work around the bug. So that will, and then there will be different tools provided.
Okay, thank you.
Good question. Other things, folks, you have in mind? Okay, I will also talk about in details about some of especially the classes on the left hand side, and we can also have more discussions there. So yeah, so 151, 251, oh, sorry, 152, 252, this is a computer architecture class. Some of you may have already taken this one, some of you are taking this concurrently, some of you are planning to do that next spring. So this is a really cool class. We talk about most of the basic architecture component. We'll only focus on the inverter course, but this class will actually get into more, this is actually how auto ordered core works, right? How the modern processor works, superscalar vector processing, GPUs, multi-threading, cache coherence, memory hierarchy, virtual memory, all of those will be actually mentioned there. And in this class, you will also be experimenting some of the infrastructures, Berkeley debug, especially RISC-V infrastructure, Chisel, simulation tool, Spike simulators, and the folks running this class also modernize this class so that you will be using the chipyard infrastructure to build some understanding on the SoCs. A lot of the labs will actually give you a perspective on doing design space exploration. So far We haven't done too much of that. We are mostly thinking about individual design points, but in 152, 252, you will actually see a lot more on what are the different alternatives, how you compare different alternatives, how different things interact with each other with different, let's say, cache size or different vector widths, how that actually eventually impact the performance of the application. So that design space exploration aspect is also very important, and you will also get that from 150 to 252 in that class. Load-wise, my sense it's actually lighter, slightly lighter than this class, not a significant project component, especially for undergrad, but a lot of understanding those different microarchitectural features and the lab doing design space exploration. So that's 152, and Brenda is wondering, the Bring Up course is being offered fall 2022, but it's not. Yes, that's the case. I actually just checked. I checked with Bora yesterday or 2 days ago. He plans to offer that class, but somehow it's still not listed yet. But that the fall is the plan to do the Bring Up class. Okay, yeah, so we'll keep an eye. I also keep an eye on this. I told Bora some of our students are very interested, so he's aware of this, and he thinks it's a great idea to actually have students who haven't done tape out to do the bring up first, so that you folks can see what kind of features are useful. It just I'm actually not sure why it's not enrolled. I wouldn't worry too much about the enrollment. I think you folks will have a seat. It's more just logistically how they manage to get this course listed. So this is 152, 252, the architecture class. It will be offered spring 2023. The next class is also will be offered spring 2023. Is a 251B. So this is also a direct follow-up of this class. And we'll talk about advanced digital circuits, but we have already been, I'm co-teaching this class currently this semester, and I will be teaching this class again next spring. So we have been actually, it used to be 240B, if some of you know the history of the class, mostly focusing on the circuit design component, but we did add a lot more system C component, how we do actually interconnect, how we use actually chisel, and we also add high-level synthesis actually to do more than instead of Verilog to do hardware design. How we actually design the SoC and take advantage of the chipyard infrastructure to build RISC-V based SoC, and then how we run different tools to actually do power area estimation and also do more optimizations there. So this will be, if you folks are interested in actually going deeper into hardware design and see how different components actually go through the design process, not only just for function, a lot of time, so far we're mostly for functionality and the performance, right? Latency is very important. We'll do a lot more power analysis, making sure our circuits or our system are actually optimized to do efficient processing for both power and performance. We'll cover a lot of the topic there. A lot of the tools that you will see may be actually more aligned with some of the tools that you have seen in the ASIC lab, but also go a little bit deeper. We'll also cover more tools, and also sometimes we just take those files by default, right? Like folks in the ASIC lab, you see a bunch of like the library files. We'll also go deeper, like what those library file means. How do we actually use, edit, or modify, or create those library files? So we'll also go a lot deeper. But even you haven't done ASIC lab, it's okay. Like IPG lab students, you are also very prepared. You will also will get you started to see the different infrastructure side. So you will see Chipyard, which is our RISC-V ecosystem. You will also be using with playing with Hammer. ASIC lab students probably already have seen that, but we'll also use Hammer, a lot more advanced features of Hammer to actually do more other components, especially on low power design. So this is a really cool class where also we're revamping or adding new system C component onto this class. This is another very hands-on class. You actually do a lot of those, basically understanding the topics, but also using the labs to actually go deeper into more than SoC building. So this is also a good class. It's listed as a grad level 251B, but undergrad, if you have taken this class, you are prepared, you meet the prerequisite. Just reach out to me whenever we start the course enrollment, and I'll give you a enrollment code. So this will be offered spring 2023, and I'll be teaching this. This will also be a fun class if you're interested in the hardware component. Any questions? Okay, so we already actually mentioned that part of the thing that we'll be doing in 251B is basically to do the complete SOC, right? And we mentioned a lot of infrastructure will be like, you folks have already used a lot of infrastructures, right, in this class. Both Vivado for ASIC lab, FPGA lab, and Hammer for ASIC lab. In 251B, you will see more. In particular, you will see the chipyard. It's also our infrastructure broadly used even outside Berkeley these days in how we can attribute a RISC-V based SoC. So we'll cover that. You'll actually be able to use, everything's open source. You'll be able to use that in your future design as well. We'll also use FireSim. This is also a Berkeley infrastructure, also publicly available, where we can actually use AWS FPGA instances, F1 instance, to do actually FPGA-based simulation or emulation. Many of you probably already know, like we talk about FPGA, a lot of FPGAs used in like this like field deployable like signal processing, right? But another major source of FPGA is actually being used is actually in the cloud. So AWS hosts their cloud-based FPGA, their F1 instances, where you can actually use FPGA Xilinx FPGAs there. And Microsoft Azure also has their FPGAs. Currently, I need to double check, but my impression is mostly for internal users, but they may also open up to external users. So they also have a lot of very good high-end Altera FPGAs for different emulation and special domain-specific system design, right? So you will also in 251B get exposed to this kind of cloud-based FPGA and how we can actually use FPGA to test whether our system works or not. We have this FPGA emulation guest lecture at the beginning, like the first half of the semester, right? So a lot of emulation, you will also get that experience where you're not using FPGA to do a particular design, but you are using FPGA to simulate your design to catch whether you have any issues in the design. So it will also be infrastructure side where you get to see our infrastructure, build complete SoCs. A lot of our students, especially undergrad researchers, they get interested after taking the class. They want to be more involved, and taking this kind of more grad level courses is a great way to actually learn our infrastructures. And then while taking this is also a good opportunity to be more involved in research. See some of the research side. I mentioned like this kind of infrastructure is basically what we are using for our research, right? After taking those courses, you will also be very well prepared to use those infrastructures in a research context and see a lot of more open-ended things that you can do here at Berkeley. So this kind of infrastructure will also be covered. We'll also be introducing those infrastructures in this class. So that's 251B. There is another class, advanced topic class. I wish I can teach next semester, but unfortunately I don't have the bandwidth. It's 292 hardware for machine learning class. The most recent offer is spring 2021. All the course material is actually online, including lectures, recordings, labs. I love this class. This class typically, I think half of the students are undergrads, half of them are grad students. It's more like a special topic. It's very open-ended. We are interested in hardware machine learning, what it really means, right? What are the technical challenges? What are the infrastructures? And what are the opportunities there? It's a very good way to really systematically think about domain-specific hardware, how we think of both hardware and application, and how we work together. And we always have guest lectures. I mentioned a lot of this area is very interconnected. A lot of hardware, software, system companies are very interested in this area. So I really enjoy teaching this class. Just unfortunately, I don't have the bandwidth. So this class will not be offered next spring. I may offer this again in the near future, maybe more like spring 2024. I don't know yet, but if you're interested, I do get emails from students both here at Berkeley or actually outside Berkeley. They basically just follow the material online because everything is actually online. You can actually do the lab. do the homework, and also go through all the lectures there, right? So if you're interested, you can also do that. And again, this is also another class. If you go through the material, you're very prepared to actually play with a lot of, get engaged in a research topic in our group. So even this, unfortunately, we cannot offer this class next spring, but if you have time, or maybe over the summer, just go through the labs. Labs are pretty, it's not too heavy. I think most of the students are able to finish that in a week. So it's not, I think it's probably comparable to the labs that we have in this class. A lot more infrastructure, and we'll be using both TripYard and FireSim. So you also see some of the research infrastructure side. So you should be able to follow the lecture and the labs on your own. But it just, unfortunately, we don't have the bandwidth to offer this class again next year, but it may be offered later. But if you're interested, all the materials are online. You can take a look. Questions about, I guess, 152, 251B, and 290 classes, at least 290 that I'm aware of. Clear? Okay, well, let me know if anything come to your mind, and that all those are very good ones. Two of them will be offered next spring, and this one, other resources are publicly available. The next one I do want to mention is a tape-out class, and this will be offered again spring 23. So I strongly recommend, if you're interested, to go definitely take this class. I wish I had the opportunity to take this class when I was an undergrad, right? And this class I briefly mentioned. I guess a couple of weeks ago, the latest enrollment I heard, well, it's already the end of the semester, but like almost 40 students actually stick to the end of the semester. And what I heard is like all of them actually have multiple offers. They're basically either full-time or internships. They're basically talking to different hardware, software companies just to decide where they want to go. But that skill set is highly desirable. We talked to our industry contacts. They are just so impressed with our students and things that our students are able to actually build a tape out undergrad, do a tape out in a semester, and all the things that they actually learned in that process. So great class. If you enjoy 151, you will definitely find things that you like in this tape out class, and you'll also go a lot deeper because you actually need to fabricate this, right? So this is actually, so now we are actually going to use Intel's process instead of TSMC. So you will actually go through a very good, this Intel process is actually pretty good. You will go through this process to design a very complex SoC. So this semester, what I heard, they're already doing 2 versions, like previous semester only 1 chip, this semester actually 2 chips. We may actually even have 3 chips. Actually, I was actually thinking we should actually do maybe some of the research topics. We should also put it in a paper class to get students to explore a little bit more. So this is really cool, and I think this is a good way to see what kind of things are actually involved, and you will also be divided into different teams. You also need to learn how to interact with different teams and how to actually make sure what you need to do is actually on schedule. So it's a really good class. I highly recommend it, and if you can fit this in your schedule, definitely do that. And then together with the bring up class in the fall, you can either do the bring up this semester, this coming fall, or next fall 2023. It's up to you. This combo is really good to get the real world opportunities and experiences. Any questions about this set of classes? Okay, so I think I talk a lot about the courses. We are always interested in growing. I'll talk a little bit more about some other, I think those are like the hardware related courses that we are growing, and we try our best to have enough staff to support this. I'll talk about maybe some of more like the peripheral courses related to hardware. Those are also good to take. Before we get there, one more thing. A lot of our grad students actually really want me to bring this. Some of the ASIC lab students, you folks know Dima. Dima has done actually a lot of work working our group, doing a lot of actually more also domain-specific accelerators. So Dima also mentioned like Dima would be very interested in actually also working with undergrads. So if you folks are interested, also let Dima know. Our group very interested in like hardware design and the integrated circuit in general. Most of our designs are actually focused on the digital. We don't do a lot of analog design. We definitely interact with analog design, but we don't do a lot of analog design. So your background are actually perfect for our group, because our group is actually mostly focusing on the hardware, digital component, and also architecture. We're also very interested in domain-specific system. We have a lot of foundations in RISC-V design. We also, especially Chris's group, has also been doing like more than out-of-order processor design, the boom sequence, and also like the vector extension, right? There are also the vector processor is also being developed. Like my group is actually very interested in domain-specific architecture. We have done a lot of work in the machine learning front. That's why I'm also like a lot of the topics in hardware for machine learning, the 290 class specifically also relate to our research, and we actually use the research infrastructure we developed to run that class, right? So machine learning is definitely a driving application, and we still have a lot of work in this space. We're also very interested in emerging application. I mentioned Dima, right? Dima is very interested in robotics, right? So that's also an emerging area that we also grow very, very quickly in the past couple of years. So we like to see how we can actually better understand the application, understand the hardware implications, and then we can do this kind of full stack exploration to design efficient systems. So if this kind of topic interests you, let me know. I'm always very interested in, especially getting undergrads involved in hardware research. After 151, you are very prepared. You can either take the courses to get more familiar with the infrastructure, or get involved in research to see how you can also contribute to some of those ongoing projects. If this kind of project interests you, definitely let us know. We're also very interested in like some of the hardware software code design aspect, how we not only design better architecture, but also better algorithm to improve performance and efficiency. The new Slice Lab plus previous Dev Lab, we also very focused on the design productivity, right? How we can improve the design process. I mentioned the Chisel project. We're also very interested in high-level synthesis, right? How we can bring the design abstraction from Verilog to something higher level, so that we can make the hardware design process easier and more productive. So that kind of topic is also on our radar, and we are also very interested in growing that area in the next couple of years. So I always make the pitch, and typically right after I make the pitch, a lot of students reach out, and then after either the winter break or summer break, not a lot of students stick around, which is fine. I think that's just part of the process. You folks have your priorities, different things going on. If anything, what I want to mention is that we like to get you folks involved, and if you enjoy what's covered in this class, I'm very sure you will also enjoy a lot of the research exploration. Let us know. Also, let us know your bandwidth, and we can strategize different, like some are like more semester-long projects, some are like more months-long project, and really get you started, get you exposed to some of the research opportunity. You don't need to actually like, oh, I want to do grad school, that's why I want to get involved in research. That's not really the way to think about it. It's more like if you enjoy the topic, you want to see more, taking more classes is one way. If you have extra bandwidth, getting involved in research is another way, right? So reach out to me directly, or reach out to GSIs. Like you also see a range of like this year, all 4 GSIs are grad students, right? So you already know them, right? You know their topic. Just talk to them and see what they are interested, and whether you can actually get involved in research. So that's I guess the courses and also some of the research opportunities I like to mention for folks who interested in those topics and also want to see more of hardware design, get more involved with while you are here at Berkeley, because we are very interested in give you that perspective both from teaching, from courses, but also from research. So if you are interested in participating in research, let me know. I guess one last note, I also always mention that this is towards the end of the semester. You are very busy with your project. It's just by no chance, it's unlikely you will get involved right now in research, right? So you don't need to feel like, oh, I have to actually get started now. Just if you're interested, let us know. I think more realistic speaking, after the summer, when you return back from internship, from your vacation, and then you want to be more involved, we can talk about how we get you involved in the fall. So that's, I guess, the different plans. And one more thing I want to mention, I will be teaching this class again this fall, and I'm looking for undergrad GSIs to run the labs. If you're interested, if you enjoy this class and you want to actually also share your excitement and your passion to the next generation of students, next batch of students, let me know. We always look for GSIs, UGSIs, and both undergrad and grad students to run our labs. Okay, so that's courses, research, and the teaching things coming up after 151. Any questions? Anything you have in mind? Will is asking what's happening. We are talking about what's next after this class. Okay, I guess things are clear. You know who to talk to. At least that's basically the most important part. Finally, I like to always end my class with some of my thoughts in this space and what kind of things you can do, or the way I think about the hardware industry. So I'd like to encourage all of you. We talk about the specific things, right? About how to take what classes to take, how to get involved in research. What's really cool these days from hardware design is really it's not just like this kind of single layer thing. When we talk about layers of abstraction, right? It's not like, oh, if I want to be a good hardware designer, I take 151, I know Verilog, I just keep writing Verilog, and then I'll be a good designer. Especially for all of you folks, right? You have done a lot of interesting things, and you'll know actually a lot of things. You have taken a lot of both lower division and upper division classes, right? Moving forward in terms of really thinking about how to be more like a leader in this industry, how to actually think about where your career goes and where this industry goes. It's really important to what I call here become a modern Renaissance person. What do I mean by that? When we think about hardware designer, it can be very limited. I think that's sometimes when you think about hardware, oh, it's just doing hardware. Maybe sometimes it's really exciting you, sometimes it's not, but it's just very like single dimension understanding about hardware design. But really, especially modern hardware design, it's really fascinating just what kind of complexity involved. I'm always, whenever I think about hardware design, I was like, wow, this is crazy. This is not only just like doing my own thing. I actually need to figure out a lot of things to actually making sure I can do my things well, right? It's not, of course, I need to have my own area of expertise, but I actually need to understand a lot of things to deliver a good product, deliver a good piece of hardware in the end, right? So if anything, towards the end, now you folks are really master of digital design. You learn a lot of things through this class, right? But if anything, I want to end you, leave you with, this is really the beginning, really, of beginning to explore the really fascinating area of hardware design, to be a very good designer, to be really a creator, right? Here, you create a piece of very unique hardware that hasn't been created before. You need to actually understand or keep learning a lot of new things, like driving application. That's always very important. Before it was like all the different like spec, there like different benchmarking, different area. Modern days, machine learning has been basically taking a lot of emphasis in doing hardware design. Like every new generation of, let's say, NVIDIA GPU have new piece of hardware focused on like graphics, ray tracing, dynamic programming, genomics, machine learning. It's just when you think about hardware, it's not only just hardware, right? You need to understand a range of applications and think about how you can design better next generation hardware that work well for those applications. So that level of understanding is very important. Compilers, right? So I mentioned there are hardware focused courses, but a lot of other courses also great to take while you are actually here, especially for undergrads, right? 164, take a look at compiler, right? That's very important. You see this kind of hardware abstraction, but compiler will be the direct layer actually interact with the hardware ISA, right? Those are actually how we program hardware. You definitely want to have users for your hardware. I don't have time in this class, but in 292, the machine learning class, both in classes, we actually talk a lot about how we map applications onto hardware. We also have like a lot of guest speakers from like this machine learning provider, like companies that are designing hardware, like TPU, Nova, even like analog hardware Mythic, right? It's really interesting. Almost all of them, we talk about their hardware innovations, but they spend a lot of time actually talking about how they build a compiler chain so that users can actually use their piece of hardware. Like compilers definitely very important. And you have time, you have bandwidth, and that's also a good class to take to have a very good understanding operating system, right? 162 is, I mean, it's also a very demanding class on its own, but it's just so important. That's really how we actually manage the resources in the hardware, no matter which level of details you're going down to design your hardware. You need to understand how the resources are managed, how we can actually help operating system to manage system level resources, and even a lot of like power optimization techniques, right? It's really managed by operating system. Of course, some low-level mechanism is actually designed in hardware, but if anything that's actually involved with application behavior, system level monitoring, right? That we need to actually have a good OS understanding. And it's also a great time to take an operating system class during your undergrad, so you can also develop that understanding. We already spend a lot of time on architecture, digital analog circuit design, so I'm not going to spend too much time on that. Understand the devices, right? I mentioned earlier, there will also have fabrication, which has 130, also a good class to actually understand the device mechanism. I'm always very impressed with hardware industry. The entire industry is basically living on the really living with a constraint or with a premise of the end of a universal law. It's basically tell you whatever you believe in, whatever you think that actually driving your industry wouldn't last. You always need to think about how to either keep innovating to actually sustain this law so I can keep move forward, or try something completely different so that you can actually have different ideas to keep this industry going. I don't know actually any other industry have this problem. This is an industry we give ourselves so much constraints, right? So many things that we actually need to worry about. We told ourselves nothing would last. We always need to keep innovating, keep recreating, inventing, having a different version of the hardware, having a different version of software so that we can actually deliver a new generation of platform, right? So that kind of urgency, that kind of unpredictability is always there because this industry is rooted in like underlying devices, right? The device need to advance. It doesn't always advance as predicted. A lot of innovation in that area, but that kind of urgency, that kind of unpredictability also affects a lot of ways, the way we actually approach hardware design. So that's also very important when we think about, again, becoming a Renaissance person, understand the entire whole stack from very high level application all the way to understanding the devices, the fundamental principles of the semiconductor industry. And then one thing that we talk about all the abstraction, it's also very important to break abstractions, right? I don't want you to take this class and then say, oh, I'm a digital person. I only do digital circuit because I know how it works. I understand it. I wouldn't touch analog. I don't like programming. I only do what I'm good at. That's not the intention. This is really just open up an opportunity to see what you can do. You can do a lot of different things. And the really important, what will be even more important is actually to break those barriers, break those abstractions that you can actually bring in understanding from different fields, and also collaborate with people with different fields so you can actually have your own ideas and do your own innovation. So long term, what I want to leave you after this class, 151 is a great way to open up this door. You see both the hardware and software and how they are connected. But moving forward, grow yourself, take more classes, both inside hardware, but also outside hardware. Always curious, stay curious, keep learning new things and how to actually break those barriers to have like innovation across the stacks. That will always be very, very important when we approach hardware design. Related to that, I also want to share some thoughts in the way we think about modern architecture or modern hardware design, right? Another thing with, especially when we take this kind of class, we talk a lot about like the classical things, right? So this is how we do that. This is 3-stage pipeline, 5-stage pipeline. This works this way, just learn this, and this is how we design flip-flop, right? This is how we design SRAM. So I think once you take a particular class, because you'll always learn like the classic things, right? Those actually, after years or decades of exercises, decades of learning, that's what people realize that works, right? But really, one thing I also need to actually keep remind myself is that architecture is actually evolving, right? It doesn't always need to be certain thing. We learn something from textbook that actually works, at least works so far, right? But it doesn't need to always be something always super important, always super critical, and always designed in a super particular fashion, right? When we think of architecture, in reality, it is here when I use like a reflection of time, right? The time that we live in, right? It evolves with application. I mentioned like machine learning becomes so important these days, and then we design so many different systems for machine learning. Maybe some other things will become more important. Then we need to understand other things. It also evolved with technology, right? We start from like mechanical computer, right? Bipolar transistors, CMOS, right? And then planar CMOS, then FinFET, right? Then we're talking about a gate all around, right? Things are just keep changing. That doesn't make sense to say, oh, this is something that works. We'll have to stick with that. We need to change, right? So if anything, especially in the long run, when you think about hardware design or architecture, be brave, right? You need to actually build the hardware that reflects your time and your understanding. Of course, there might be some principles we learned, but they may not be applicable anymore because things change, application changes, the underlying technology have actually completely different, right? You understand why those works under a certain generation, but then maybe when you actually design your piece of hardware, it doesn't work that way, right? So that's one thing I want to also leave you with. Things will be changing, especially with what we call this kind of vertically integrated system, right? A lot of them will be application driven, and we'll also need to see what are the different underlying technology and what they bring us, right? If someone told you, oh, we already tried this 20 years ago, 30 years ago, it was a terrible idea, it won't work. I think you want to spend a little bit more time before reject yourself. It's like, oh, well, it tried 20, 30 years ago, but maybe the circumstances are different, right? Maybe it was a bad idea, a terrible idea before it can be actually a very good idea now, right? So keep that in mind, right? Don't limit yourself. We learn the things that work so far, but it doesn't mean that we have to stick with what we have. We're always innovation. We always need to adapt ourselves and try different things. And so be brave in that process and build hardware you want, right? That actually reflect your time. That's always very important. And the next thought I want to leave you with is also architecture, like we talk about time, but also architecture is really a conversation, I use a conversation with space, but it also needs to be considered in terms of what are the things actually around you. Eventually, it's really interesting to think about the computing system, right? From basically the pursuit of getting higher frequency, right? Building the fanciest auto order processor, getting super highly pipelined design, a lot of pipeline stages, getting just as high frequency as possible, building very complex order engine and very complex hardware to what we really see today, right? So you think of like Apple Silicon, right? It's very heterogeneous, very spatially distributed. It's not only just the pursuit for highest frequency CPU anymore. It's really about how we can coexist with each other with CPUs, even for CPU, we have high performance CPU, low power CPU, GPUs, right? Everybody's building their, Intel is also building their GPU, like especially accelerators for all the different applications, right? So the way to think about, I like to use this analogy, just looking at how the computing system actually evolved in the past like 2 or 3 decades is really from building skyscrapers. We want to stick with one thing and do that really, really well, build the highest frequency, the fastest auto-ordered engine, super deep French predictor, building the highest skyscrapers, to really think about actually more spread out system. It doesn't really necessarily mean we need to build the best of things. It's really about how we actually have a system with a range of different components, and each component are kind of doing good. Like maybe we have high performance CPUs, but we also have like energy efficient CPUs that can do more housekeeping work very efficiently. We have graphic processors, we have machine learning processors, we have video codec. We have a lot of those different IPs. They're specialized, they're doing well with what they are designed for, but maybe not for other things. But then they coexist, right? They're like different paths. They're very well connected. That's why I use this kind of huton, like it's just like I said, for folks who are less familiar, like a Chinese style, it's just like super thin, like small road, very spatially distributed, but also very connected, like a small ecosystem, right? So instead of building this kind of tall skyscrapers, it's really about how you can coexist with a lot of other things that design for different things. So in retrospect, it's really fascinating to think about modern computing system from like single thread doing super high performance into this kind of spatially distributed heterogeneous engines coexist with different things and making sure at the system level they are collaborated, they can actually work together. Right. So with that, under the theme of actually also think about the space, right? So when you think about hardware design, it's also understand not only the piece of hardware that you have been considering, you are designing, you are leading, but also keep a system perspective, understand what are the other neighboring units, right? You are designing maybe, let's say your cache system, you need to have good low latency, high bandwidth, but you also want to take a look at what the course is trying to do, what the applications are running, what kind of level last level cache actually shared, what kind of traffic it actually exists in our system, right? So understand your neighbors, right? Understand as much as you understand yourself. So that's also very important in building an efficient system, because now things get a lot more heterogeneous and get a lot more spatially distributed, right? So things will be specialized. You may actually be assigned, or you may actually be like, maybe you are doing your startup, you actually have a very new idea in particular engine, right? But always think about what are the other things that will be actually surrounded by your engine. That's always very useful for the long-term success, both career-wise, right? How you lead a big organization, lead a big team, very diverse, focusing on different aspects of the computing. system, but also how you develop really a good system that actually can deliver good performance and efficiency under a range of different scenario, right? So architecture is important. It's about what actually needed given a particular time, right? But architecture is also about how you coexist or how you interact with your neighbors, with other engines, other teams. That's also very important to build efficient system. So the past 3 slides, if anything, I'd like to leave you. We have this class, we open up with a lot of opportunities in hardware design, but first always remind yourself you want to, especially during your either you're a grad student or undergrad, right? Or this is a great time to learn things. Definitely learn more. Don't be constrained into your comfort zone. Reach out to other topics and also willing to actually break those abstractions that will actually be very important for you in the long run. Second, you don't always need to stick to whatever the golden principle has. Like 20 years ago, nobody believed in domain-specific accelerators, right? Like general purpose is always important. 20 years later, this is basically the way people are building hardware, right? So you can have your own idea, be brave, propose your idea, keep an eye on what things are actually changing, either technology or application, and be adaptive when you think about hardware. And finally, I think the future system will be much bigger, spatially distributed. So with that, don't be too comfortable with your own design, but keep an eye on like other designs, other components that could actually lead to very significant efficiency and also benefit of the entire system. So again, 3 slides, 3 message. I also, every time I actually think about this, I also remind myself in the way I think about hardware. So I also want to share those with you as something to think about moving forward. So with that, I think it's come to an end. I also want to take this time to thank our GSIs, Alicia, Dima, Sia, and Equan. This is a great new team. I actually for especially Alicia and Equan, this is my first time working with them, and Dima, this is actually Dima's first time actually teaching here at Berkeley, and Sia actually got involved very last minute, actually after the semester started, because we have so many of you interested in hardware design, and we really want to actually have enough staff to help you, right? So we managed to assemble a great team, and I'm very grateful for all the efforts they put together in helping me and hopefully also helping you to make this a learning experience a fun process. And this is not really the end. They will also be helping you towards the end of the semester, especially with a project and also with a final exam and prep. So, but I really enjoy working with them. They are basically the best teaching staff I've worked with. One of the best group of teaching staff I've worked with recently. If this class is successful, it's all because of them, because they actually put a lot of resources and their experiences in managing this class. So I want to thank all of them to actually be here working with all of us and bring this very unique experience. And finally, I also want to thank all of you. This is a challenging course and in a challenging semester. I mentioned I didn't expect we will also conclude this class the last virtually. I was definitely not prepared for that, but it's great to see you all here, get to know all of you, register your face with your name, and having conversation with all of you, either during class and also during office hours, or even just having hallway conversation. So thank you very much for joining this endeavor. And I know this is a challenging class. All of you are working really, really hard. And if anything, I think I mentioned before, just power through the last 2 or 3 weeks at this point. Definitely take good care of yourself, but you have really accomplished a lot. And push, if anything, I think you will accomplish even more and in the next 2 or 3 weeks. So push definitely give yourself a little bit push, but also feel very good because you have accomplished a lot and you are very, very close. If you have any other issues, I already have several conversations with some students, reach out to me, right? We can help in any way we can, right? Don't always reach out, don't get isolated. This is really a team effort. So let us know how we can help, but definitely we are very close. This is a challenging semester, but I personally had a lot of fun. I think this is actually the semester I enjoyed most in the almost 3 years here at Berkeley because all my previous semesters are basically a virtual semester. So this is my first full in-person semester, even we have a couple lectures actually virtually, but I really enjoyed it. Thank you, all of you also bring me that perspective and this very unique experience. I had a lot of fun. I hope you also have a lot of fun. If anything, I mentioned this industry is crazy. This industry is basically always assume this is the end, something we cannot deliver the next generation product, but we always manage to deliver the next generation product, right? So I think we always try to scare ourselves, keep ourselves alerted, but manage to power ourselves through with crazy, novel, interesting ideas. So with that, my last message for you is also stay curious and stay optimistic. There will be a way. There are a lot of things you can do in the future. I'm looking forward to hearing all the amazing things of what you will accomplish in the future. With that, this is the end of the class, and also this is the end of regular lectures of this semester. Thank you all for joining this journey. We do have a guest lecture next Tuesday, so join that guest lecture. It will be fun to learn more system Verilog. But other than that, always reach out to me. I'm available. Send me an email, Piazza, reach out to me, anything I can help. With that, let's keep in touch, and good luck everyone with the rest of the semester, and let's also stay in touch. Take care. Bye.